Hola, buenos días a todos. Vamos a esperar un minuto más para empezar la conferencia. Se están conectando muchas personas, así que trataremos de esperar lo más posible. Espero un minuto, 2 minutos para poder empezar. Como les habíamos comentado en el chat, la conferencia va a ser en inglés, así que ahorita vamos a hacer la presentación del doctor Vittorio Lippi. Esperemos un minuto y comenzaremos. Okay, good morning. Thank you very much, Vittorio. We are really happy you accept the invitation to be part of this conference. Now, let me share with the audience some of your work. Vittorio Lippi is a roboticist. His research includes human and humanoid posture control, human robotics interaction, gesture recognition and learning by demonstration, machine learning applied to robotics, nuclear physics, experiments, and industrial process control. He's a computer engineer, and he got a master's degree in industrial automation, both in the Università di Pisa, and he's a PhD at the Scuola Superiore Sant'Anna in Pisa, Italy. He has published many peer-reviewed works on journals and conference proceedings. Currently, he works at the Uniklinik Freiburg in Germany on benchmarking for exoskeletons and humanoids and human posture control. He was a CEO and founder of the EUROBENCH in Fano, Italy. Vittorio was a visiting researcher at the Fermi National Accelerator Laboratory in Batavia, USA. He developed a method based on supported vector machine classification for the rejection of multi-jet background in a hadron collider environment. In 2008, he got a position of research assistant at the Scuola Superiore Sant'Anna in Pisa, Italy, at the Perceptual Robotics Laboratory, involved in development of virtual reality platforms for the transfer of skills and development of algorithms for diagnostic of anomalies and system failure. He was a postdoctoral researcher at the Universität Freiburg in Germany at the Neurocentrum Posture Control Laboratory. Vittorio, thank you very much to be here, and you can start the presentation whenever you want.
Thank you for the introduction. Hope everyone can hear me. I can start sharing my screen. Okay, hope see my first slide. So thank you again. Thank you for joining this meeting. The topic of my presentation will be the identification of neurological model using machine learning. As it was introduced, I am working, working at the University Clinic of Freiburg, so in the Department of Neurology. In general, we are both an hospital, but also a research center about neurology and neurophysiology. And our specific research group is the posture control lab, so where we study both neurology and robotics. So our group applies a neurorobotic approach. That means that we have model of human sensory motor control, and we embody this model into posture control robots. So specifically, what we do is we study how humans are controlling their posture and their balancing. So we can program a robot to model the same behavior and use the robot as an experimental device to use to test our models. And then from this, we can have inspiration from both neuroscience and robotics. Specifically, our robots are anthropomorphic robots, so humanoids with joints in the legs and the torso that are designed to reproduce human posture control. We use different kind of robots, like some, like our postdoc 2 was actuated with pneumatic muscles. And then we have a newer robot, is Lucy, that is 40 degrees of freedom, and it is actuated through DC motors. But in both the cases, we are controlling the robot with torque control. You will see that later that our models are pointed to control the torque in the joints. So you say we had models with pneumatic actuation and DC motors, and these robots were built through the years to cover different models of human posture control. So the oldest one, Posture 1, it was a robot with 1 degree of freedom, so a single inverted pendulum that represents human balancing in most of the cases when the disturbances are not complicated. Then we built a robot with 4 degrees of freedom, so we had 2 hip joints and 2 ankle joints. So with this robot we can do double inverted pendulum posture control, but also simulate leg swing. And then our latest robot is the UC robot with 14 degrees of freedom. So in this case, we can also control the knees, have 3 degrees of freedom of rotation in the hip joints, and we have also degrees of freedom in the torso. So with this robot, we can test also squat motions and balance in the frontal plane. So as I said, this kind of modeling is also an inspiration for robotics. So here I can show you an experiment we did with a robot from the DLR, the German Aerospace Research Center. Probably you know this robot if you are into robotics, because it's a famous toy robot. And you see here we applied our bioinspired control system to the balance of the robot, and in this case in the sagittal plane. And as you can see, applying this human-inspired control, we have the robot balancing on a stable surface and also compensating the external disturbances that was the person touching it. So our models, our human-inspired model starts from the idea that the human body is a real body subject to physics, and then human sensory motor system has several sensors like spindle, Golgi tendon, like feeling skin motion, from which humans are reconstructing some physical quantity describing the state of the body, so like joint angle, joint torque, also the position in space using the vestibular system, our equilibrium sensory input. And then, like from this reconstruction, we can reconstruct, we can sense which are the effects that are impacting on the body. So we distinguish 4 physical inputs, like an external contact force, like we have also seen in the example before, like field forces like gravity, and the effect of support surface translation and support surface tilt. So we divide the effect of the external world on the body in these 4 physical effects that are perceived by the human sensor fusion, but also they are acting on the body. Like if we model the human body as a single inverted pendulum, we see that these forces are mapping on the ankle torque, like, and should be compensated for the body to stay, like to maintain posture and balance. So if we from this we make the hypothesis that the humans are using the sensory input that we have seen to reconstruct these external disturbances. And so these external disturbances are both used to perceive the state of the body, but also to compensate them and to allow the body to balance. So we, from this, usually to test this, we propose some stimulus modalities that are touching these kind of external disturbances. So like having the human standing on an hexapod, and we have a supersurface rotation, supersurface translation, and also body pull, We have also some more advanced stimulus that we are testing in our lab, like body sway reference, where we take the sway of the body and we move the platform according to it, because in this case, then the angle of the ankle is always 90 degrees. And if you think about the sensor fusion, we have seen it before, it's like taking away a sensory input from the sensor fusion. And we see that humans are able to balance in this case anyway. And so when we produce a robot model to control the robot, we want the robot to be able to perform also in this scenario. And then we can also test visual input like moving the scene, and we have also more advanced things like having stroboscopic illumination to let the user perceive position but not speed, and so on. And from this kind of experiment, for example, if we take supersurface rotation as an input, then we get like an experiment from testing the human with supersurface translation. We get this kind of response, this kind of description of the human posture control. Like we use as an input usually a pseudo-random signal, so that the human cannot predict it, and we have a pure reactive behavior. So we test different amplitudes because, as you will see, human behavior is non-linear, and we will see it. And then having this movement as an input, we can characterize body sway, like so the sway of the center of mass respect to the ankle joint, and we can characterize it in frequency. So we compute the frequency response function. It is a empirical transfer function, and between the tilt, the disturbances, and the body sway, and we see how the humans are behaving. Taking several subjects, we take some responses, so we see how the humans are behaving in frequency. So in this case, we can see the humans are have a nonlinear response. So they have bigger gain when the signal is smaller. We can see they have a specific phase profile, and they have a pretty high coherence, but it's not one. So the coherence is a measure of the linear dependencies between the input and the output of the system. And we see the humans are moving because of the tilt, but are also swaying for other reasons, like noise or like some spontaneous sway. So on this basis, then, once we have this description, we try to model it. We propose a model that is called the DEC, the disturbance estimation and compensation. This kind of model is based on the idea of the hypothesis we have seen before. The humans are performing a sensor fusion. So we get several sensors from the state of the body, and then we compute the 4 external disturbances. So the external torque, the surface acceleration, the gravity, and the foot in space rotation. As you can see, in our approach, the gravity is considered an external disturbance. In a lot of modeling is considered part of the model, but for this specific purposes, we consider it something that humans are identifying and compensating. So we produce a model. We model that has some parameters, some gains in this feedback system. So it's like a model with a compensation of the external disturbances. So it's in a feedback loop, and then it has a servo loop with a neurological control that usually we model as a PID. So what we see is that when we apply this control to the robot, we see that we can reproduce a similar response. Oh, sorry, didn't want to make these lines. Made them by mistake, these annotations, but okay. But maybe I didn't make them. So this is the response to the robot using the DEC control. As we can see, the robot, in this case, was the post-probe 2, the one with 2 degrees of freedom, is reproducing the nonlinear characteristics of the humans. It is reproducing also the typical phase, and this slide I didn't have space to show it, but actually the coherence of the robot is a bit better. But as we can see, it has somehow reproduces the characteristics of what the humans are doing. So that comes the problem of identification of nonlinear system. This is the topic of this presentation. Like these postal control systems are nonlinear. So in the general case, the identification, once we have experimental data with humans, is performed with iterative algorithms. Like the idea is to use neural networks that are expensive to train but cheap to use, in the sense that once we train the neural network on several examples, the computational cost of identifying the parameters from a single experiment is very low. It's something almost immediate we can use also in a clinical setup almost in real time. And then we use our parametric model to produce the training set. So the idea is to take the DEC model, like we have seen before, where we have several components, like we, in this case, we still think about the body as a single inverted pendulum. So we study the sway of the CIM, of the center of mass, and we take this model and we try to identify the parameters. As you can see, being a bio-inspired system, we also lamp delay that represents all the neurological delays that we have in the body. And actually, also in robots, we have an amount of delay usually. So from this model, we get a control equation, like including all the components, the identification, the compensation, some modeling of the passive torque. We get control law that is like mapping the state of the system, like to the torque that we want to apply on the ankle. And in this control equation, we have several parameters. So we have the delay that we have to identify. We have the coefficient of the neural control that is modeled as a PD. And then we have also nonlinearity. This nonlinearity is like represented by a threshold, and if you can see, like the group of the system of equation in 3 represents this threshold. So we have a threshold theta, and within this threshold, perception of the support surface rotation is 0. It's like we assume that the subject or the robot is not perceiving it. It's something we observe experimentally. And outside of this equation, instead, it is like going up, I mean, linearly, but starting from 0 at the end of the threshold. So we have this is introducing a dead band, but also gain nonlinearity. And then we have a noise, like we model as a Gaussian noise, that is the vestibular noise, and we want also to identify these. And then we have two components that are the passive, that are like Kp and Kd of the tendon of the body. And these are like more or less similar, like a PD, like the neural controller, but they are not affected by the delay. So because they are a mechanical effect, like stiffness and damping of the joint. So when we think about identifying this, so what we do is, like in our simulation, we simulate the body with the body's way, having the input as this pseudo-random input that we have seen before. We use it to perturbate the body, and we take as output the body's way, like the body's way of the body. The human body is modeled like with a biomechanical system, like we used to simulate humans. And then the body's way is recorded. And then the idea is to use the neural network we used to identify, taking the body's way of the human, or like of the subject we simulated, as an input. That's why here this is as an input. And then take the parameters that have been used to simulate it as target. So we have a neural network that looking at the input, like the sequence that is a body's way, gives us the parameters that are producing this kind of behavior. like the PRTS, this pseudo-random input is kept fixed for all the simulation. So it's like we assume that when we want to identify the body, we use that input, at least in this example. But in general, one may need to use different inputs, for example, to emphasize the nonlinear effect. But in this system, we assume that is always the same input, and we look directly at the output. So we have some standard parameters we use to model the system, like that are used to reproduce human behavior in human studies. We take those, and once we have these parameters, we generate a distribution of parameters for the simulation. So the neural network we use takes as an input a picture, because we use convolutional neural network. So this is a technology used to mostly to identify pictures, like to work on pictures, because the convolutional neural network has the characteristics that it is using some group of weights, some group of neurons that are repeated on all the pictures and translated. So using the same weights. So what this means that to produce an input that was suitable for this system, we had to produce an image. This image was a two-channel image. So the first channel was there were amplitude and frequency of a periodogram. We are taking the frequency, the fast Fourier transform on time windows, and we are producing several, let's say, several lines. And in the picture we have two channels. Like in this example, I represented it as green and red color. They are representing respectively the amplitude and the phase of the periodogram. So it is like applying a Fourier transform on a time window and shifting this window in time. So the pictures, the coordinate of the picture represent the frequency and the time of the experiment. So the interesting thing is that once you apply a convolutional network, it is repeating itself over time, like an horizontal translation, it means that you are recognizing patterns in time, even if they appear at different time. It's not obvious what it means, physically, to translate these in frequency, how the network can gain advantage from some kind of invariance in frequency. But the interesting thing is that the best results I've obtained, trying different type of parameters, is with a square image. I even tried to have a very long image representing the time series and as a one-dimensional thing, but the best was with a square one. So there's some there is some advantage in distributing the information between frequency and time at the same time. So to produce the dataset, these random parameters that were sampled with a uniform distribution were simulated. So simulated means we are simulating this single inverted pendulum balance with different gains, delay, and what we have seen at the beginning, if you see, for not all the simulated, not all the simulations were producing a stable behavior. For example, if the control gains are too small, or the delay is too large, the system can become unstable. So in the simulation, we were just using simulation that were producing a stable behavior. So it means the subject was not falling for a simulated time of 2 minutes. And what we have seen is that a lot of these simulation had a very small peak-to-peak amplitude, in body's way. So it was an interesting fact, because humans usually take the compensation of the standard teeth a bit in a relaxed way. They don't really try to have zero body's weight to compensate fully, but knowing that they can stand this kind of disturbances, humans are usually allowing themselves to sway. So what what we have done here was to take some simulation that were producing a larger peak-to-peak amplitude in the body's way, and try to simulate again them with a slightly modified set of parameters with smaller modifications. So in this way, we enriched the system with some, you see this orange data set in the histogram. So you see, we enriched the data set with a larger body sway. So we have something that was more human-like. And during the training, like we used as loss the mean square error, and we were using a training set, a validation set, but mainly they were providing the same result, because this simulated data will appear to be really consistent. Like and then to show what this means, like you can see the prediction or targeted, like on this picture above, you have the parameters that were identified. You see there is a small error between the two, and here you see the body's weight that was produced under the picture on the bottom. Like you see that mostly the subject was swaying in the same way in both the cases. So to quantify it in a more quantitative way, we can say that we produced 20,766 samples, and we divided them into equal sets of 6,378 for the training set and the validation set. So the validation set loss was MSA was 0.28. The training set loss was, of course, a bit smaller, like 0.22. So, but we say that with the variability of simulated numbers, we don't have the problem of overfitting in this case. And then we also tried some more other tests, not just to try again the system on the simulated data, but we tried to simulate it to check how the system was able to identify other kind of body sway. Like first, we made a simulation with a double inverted pendulum. So in this case, we had the IP, like a more complicated model that was able also to move the hip using some human-inspired parameters. And we have seen, if just taking the body sway of this system, if the system was able to identify the parameters of for the control of the ankle joint. Also, because we say that real humans can be modeled as a single inverted pendulum, but actually have way more degrees of freedom. And what you're seeing is that you see here the identification is making some errors, and also, but still it is reproducing the kind of sway of the robot. We can also say that since as input for the neural network we use the Fourier transform, somehow the system is pointing to check parameters that are producing the same frequency content over the time, not to bring to zero the error on the single sample. And then we tried also to identify human body sway. We get this data here because we didn't have a target data because they were real data. And what we see is that we get a prediction is almost following the human, but in this case, okay, the system was a bit more exhibiting a bit larger sway. So we can say that as a summary on this 1 degree of freedom example, that I mean, we can use this method for post-control parameter based on convolutional neural network. The system provides an efficient way to fit a model on a nonlinear inspired control system. And it represents an advantage to the previous solutions that we are using that were based on iterative methods. And also we have seen that, I mean, the SIP model we propose can be within a certain limit able to describe also the double inverted pendulum case. So also we tested it also for the deep. So we can go on and think, okay, this was 1 degree of freedom, but what happens if we have a model with more degrees of freedom? And consider is the deck control, the one we described, is as a structure that leads to a modular control. So we can have a feedback loop like the one we have seen for the ankle, like repeated for each module. So we can imagine the deck control extended to a modular control system as a set of modules that are exchanging sensory inputs, so like performing distributed sensor fusion and producing the torque on each joint. So in this model, we see we have a humanoid balancing in the sagittal plane, and we have three modules, like the one controlling the ankle, the one controlling the knee, and the one controlling the hip joints. So it is like each module is compensating the external disturbances, and it is balancing the center of mass of all the segments that are above. As we see, actually, so we have the same structure like we have seen before for the single inverted pendulum, but repeated for three segments. So in this case, we also try to identify an eye in the PID, because we have also, yes, an integrator in the loop. So in this case, we consider each single joint, so like the sway of the center of mass above the given joint, and we compute a spectrogram. So also in this case, we are transforming the sway in a picture. Like here we go more in detail. But since in this case the system is not always the same input, each module takes as an input the tilt of the segment that is above. So it is like for the foot, for the ankle, the input is still the supersurface sway, but for the knee, the input will be the sway of the shank, and for the hip, the input will be the sway of the leg, while the output will be the sway of the upper body, of the flank. So for each module, we have an input and an output, and we produce the image having taking the spectrogram of the input, the spectrogram of the output, and the phase difference, and we produce a three-channel image with this, like with the same principle of before. Is a periodogram, so we see time, frequency, and we have a three-channel image, so like an RGB image. Then, in order to use this as an input for our convolutional neural network, we take the mean of the training set. We normalize by the variance, like we do this pixel by pixel and channel by channel, and so we get some normalized sample. Of course, when we do this on the validation set and the test set, we use still the the mean and the variance computed on the training set. So the target feature in this case, in this experiment, are a bit different from the ones seen in the single inverted pendulum. Specifically, we have the coefficients of the PID. Then we have the delay, so like this delta, this time that is representing all the neurological delays that are applied on the system. And then we also have the control variable. So it can be a joint angle or a body sway. Since this is a categorical variable, it's like one or the other, we represent in the target features +1 and -1. So we will let the optimization of the network like solve both the problems, like because we see here we have a regression problem, and here we have a classification problem. We want to see if the joint is controlling the body, like the body's weight, the center of mass, or the joint angle. So in this case, for the sample distribution, we are using a normal distribution around nominal values. Like for example, here you can see the P coefficient associated to the 2 to the 10⁻⁴ of the 2 to the 10⁻⁴ of the 10 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 to like the deviation of the P coefficients associated to stable simulations. And we see that more or less is still like a Gaussian bell. And then we can see the distribution of the amplitude. And like before, we see most of the stable simulations are with smaller amplitude. But in this case, we didn't perform the enrichment. We thought, okay, there are still enough samples at higher amplitudes. So the network structure in this case was again a convolutional neural network. So we can see it takes these three channel images, an input that is representing the input and the output this time of the function. Then it's applying several filters like batch normalization using rectified units, pooling, and we repeat this structure 5 times. Then we have a dropout layer, and then we have a fully connected layer, that is the regression layer. So the last layer works like a fully connected neural network that is mapping the activation of the convolutional network to the parameters that we want to identify. So as a result, we got LMSC was 1,366 on the training. Then the validation was a bit higher, like 151, and a bit small test set, like these were the training results. And then, but this was the total, so it was also including the categorical variable. So we see that the fit on the parameters is a bit smaller on all the data sets, like a coherent way. And then the accuracy of the identification of the controlled variable was like 85%, 86 on the training set, 83 on the validation, and 84 on the test set. So we also see that the errors are not the same on all the parameters. Like, for example, the KI was a bit higher in proportion, also because maybe the KI used in this kind of experiments are usually small and not, I mean, the system has not the same sensitivity respect to all the parameters. So they were not, the network was not accurate the same on all the cases. So we tried also to then identify human, like identify human movement and see what happens. We applied to experimental data that was it was a double inverted pendulum. So in this case, we took the subject, we were measuring the sway of the leg, like leg in space, what is called the LS here, and the trunk, the sway of the trunk. Then we identified these two. We didn't have the knee in this experimental data set, so we even if we were training the system also to identify the sway of the knee in the simulation, in this case that was set to 0. And also because in the experiment the subject was instructed to stay with the leg straight. And here we see that we can reproduce the characteristics of the subject body sway. Like I mean, maybe it's not visible that much in detail, but what we can see is that there is a bit of offset between two body sway profiles, but still the frequency characteristics is similar, like in terms of the kind of the quality of the sway that both the simulated agent and the human are identifying. So the idea is that we can use these parameters to analyze, to study the human behavior. And of course, if we look at future applications, like what we are thinking to do, like with this machine learning applied to human posture control, is to address the control of wearable robotics. So here, if we think about a human wearing an exoskeleton, we can use like machine learning in posture control in several blocks here, like both to have a model of the user that we can use for intentional recognition, and so to tune the control system of the wearable robot. But also we can use these techniques to have an identification of the exoskeleton models in details, also with the non-nominal characteristics. And once we have parameters, we can represent how the subject is perceiving the task of posture control, is perceiving the external disturbances. We can use this to regulate the physical interaction between the robot and the user, because of course the robot is helping the user, but is also producing an external force. So we want to be sure that the human is perceiving this as an help. So as a general description then of the work, I can say that all this research is brought on in the context of the COMPTEST project. So it is a test, a benchmark test stand for human and humanoid balance and control and posture control. So what we are trying to do in general in this project is benchmarking human posture control and balance and provide a score for the performance of the robot. So if you are interested in this topic, also the evaluation of humanoid posture control, please visit the website of our project, where all these techniques and also other approach to benchmarking are presented that are made available to researchers for their own robots. So thank you for following my presentation, and if there are any questions.
Thank you very much, Vittorio. It's really interesting, all the work that you have done and you have presented us. I have several questions for the audience, and I want to read these questions. Just the first question is, this model considers the physical human defects like leg despair, problems with ear stability system. It is possible to model it?
Yes, actually, this presentation was mostly about the identification, but all this work about modeling human posture control, modeling human posture control is like oriented also to the study of also impaired people. Like, for example, we have patients with vestibular loss, or we have patients with advanced age. And of course, we use these models also to map their behavior on the parameters that we know are affecting the human control. For example, we have seen in this model we had weights for associated with external disturbances that are reproduced. They are identifying using some sensory input. So fitting the model on the behavior of the patient, we can see that, for example, some kind of external disturbances is not properly compensated, or that some sensory input is not properly used. Or, for example, you have seen in the model we have also the stiffness that we know to be useful to stabilize the body, but some patients can be too stiff because of their neurological condition. So yes, these kind of models are used also. They come from the field of neurology, and they are used for neurology, so also for diseases. Like, actually, maybe I can leave later in chat some references if you want, like about studies of human experiments using these models.
Okay, thank you very much. Another one. You have used convolutional neural networks, but when you are running your experiments, have you used another artificial intelligence techniques in order to compare the results that you have got with convolutional neural networks with another artificial intelligence technique?
No, actually, in this specific experiment, I didn't use another model because I mean, I was eager to try this new technique and see how it can be adapted to human movements. So, like, also for the specific challenge of having a sequence in time and adapting the convolutional neural network to that. Like, This, of course, was no, it has the positive thing that the convolutional neural network, in a certain way, is automatically tackling the problem of having something that is repeated in time, but at the same time, it imposes you the arbitrary decision of how to transform the input in an image, in a square, like. And so in this specific case, I didn't use other system. But what can I say? I don't know. I don't. Okay, now now, like for example, relying. I don't know if you see still my screen, but if you in other cases we integrated in the control of the robot also different kind of neural networks, like.
Okay.
For the identification, for example, once for the identification of the gravity disturbance, we used and the prediction we used a linear model, so a very simple one compared to the convolutional network. So I think in general different models can be used.
Okay, there's another question. What is the best programming language that you consider for machine learning?
Like in this case, I used MATLAB because some of the simulation and also human experiments produced in the clinic were already available in the format for MATLAB, and also, so in this case for me it was easy to interface with the simulations and with the data that I already had. But in general, when searching for the performance, I use Keras and take Python as an interface. I mean, don't think it's the necessarily the top, but I would say that MATLAB was very good for the design, but it's not probably the best for the performance.
Okay, perfect. Another one. Does an information gets lost when using a spectral image in terms of frequency and time resolutions to fit the convolutional neural network?
So the information gets lost when using what? I lost the word.
Yeah, when using a spectrogram image in terms of frequency.
Yes, in a way, I mean, some informations are lost because you make a choice on what you want. I mean, in general, if you have the Fourier transform of a signal is equivalent to, is a description of the signal in time if you put it fully. But in this case, we were making some decisions about which frequencies to leave because we consider them relevant. We decided to put the difference of the phase and not the phase of both the signals. So in a way, we were losing some information on the signal, but when you do this, you somehow you hope to make the machine more powerful. So you concentrate on the body's way, for example, at the frequencies where it is relevant for the body mechanics. In this case, it was up to 10 Hertz, and so you expect that throwing away a bit of information is a sort of regularization that lets your network learn better. Like, in a way, we can say to concentrate on relevant input.
Okay, I think that we have the last one. The question said, the equilibrium compensation model has a lumped delay due to the neurological components?
Yes. This lumped delay is representing is a way to model several sorts of delays that are in the body. Like we have delays in the control of movement, we have delays also in our sensory perception, and not all the channels have the same delay. So it is like a simplified approach in modeling. Is coming to humans, but still we see that is able to reproduce human behavior in this kind of setup, like balancing on the moving platform. And like when it comes to robots, of course, we have smaller delays than humans, even order of magnitude smaller. But at the same time, we have some delay. So also in the case of the robot, we assume to have a lump delay, and So yes, we have it. And from the point of view of modeling and identification, the lamp delay is making the difference between the active control, so the neural action commanded by the neural controller, and the passive component that has zero delay because it's a mechanical thing. But that's relevant also in that sense.
I have the last one. Which hyperparameter tuning techniques have you used? Because, okay, no, yes.
Yes, so here, as hyperparameter tuning techniques, I used experiment with the validation and test set, and I was, as I said, I was not exploring all the possibilities systematically, but I was also adjusting it on the basis of the results. So, for example, as I say, one thing that impressed me is that the best input was a square image, and this is something that I produced making several tests with different sizes of the test set and the training set. So, of course, as you have seen, this network has a lot of layers. It has a lot of hyperparameters, and choosing them is a point. But here, at the end, I was optimizing them manually on the basis of the feedback I got from the. But of course, the automatic tuning of control parameters for like convolutional neural network and deep learning in general are a research topic at the moment, because there is not how can I say, an analytical way to dimension the network in the general case.
Okay. Thank you very much, Vittorio. Just, we are going to finish your presentation, and just wait, let me, okay, sorry. Okay, just we have a recognition for you. This is Tecnológico Nacional de México, Instituto Tecnológico Orizaba, gives you a recognition to Dr. Vittorio Lippi for the presentation of the virtual conference, Identification of Neurological Models Using Machine Learning, in the Coloquio de Investigación Multidisciplinaria, and signed by our director, Rigoberto Reyes Valenzuela. Thank you very much for your presentation. It was a very interesting topic, and we have many questions that maybe I'm going to send to you. Maybe in the future you can answer it. And thank you, Vittorio.
Thank you again.
See you.
Have a nice day.
Ok, bueno, vamos a continuar con la siguiente ponencia en unos minutos. Todavía faltan unos minutos para que den las 10 de la mañana, así que vamos a esperar un ratito. Gracias.
Muy buenos días al público presente. Continuamos con la siguiente presentación del coloquio de investigación multidisciplinaria CIM 2020, denominado Caso argentino de servicios tecnológicos y de producción de bienes como respuesta al COVID-19 por el ingeniero Enrique Carrizo, oriundo de La Plata, Argentina, el cual es un ingeniero de la ciudad de La Plata, Buenos Aires, Argentina, el cual reside con su familia y desarrolla actividades dentro del sistema de enseñanza superior